Yep. So let me pull that up. All right. So I have not yet started grading homeworks. I will get those graded this week. I will get the solutions posted today. Probably do that. Try to do that right after classes post 2. Those who want to get a head start on that. Trying to think what else. Lecture videos were posted over the weekend for this week. I was kind of, as I was going over those and everything, I was reminded this time last year where we were kind of at the same pace we're going last year as we are this year. Which is good that we're not necessarily going faster because of changing things up. But you know, we're going ahead of kind of the rough schedule that I have. Fine. But the point being is that, you know, I'm happy to always try to slow things down, do more example problems on material that we've covered so far and things like that, you know, instead of keeping on going on ahead with things. So just keep that in mind. If people want to see more questions about things, just feel free to ask. Now, there was a question already about the quiz, the participation quiz. Okay. Oh. Hold that up here. So, yes, were there any particular questions on it or just the entire thing? All of them. All of them. All right. All right. There it is. All right. And we're back. Just randomly does that. Just drops audio. Right, u given by this 3/2 RT plus some value t squared plus some value times R divided by T. What is the heat capacity of this gas at 359 Kelvin, right? And so, right, the heat capacity of the gas, what do we do? Yeah, right, if I want the heat capacity of this gas. Let me write out real quick. 3 halves RT. You know what? I see something here. Right, take the derivative of this with respect to temperature. This will give us 3 halves R plus 0.042 T plus minus 1643 R over T squared, right? And that is equal to the heat capacity at constant volume for this material, right?
How are we supposed to know which R to use?
Yeah, so basically, right, heat capacities are joules per Kelvin is the unit of heat capacity. So we want to use the version of R that's joules per Kelvin mole. So you want to use R equals 8.314. That's units joules per Kelvin mole, right? The other version of R you would use, basically in this class, if you're dealing with like an equation of state for a gas, like the ideal gas law, PV equals nRT, then you'd use the value of R that you typically see in like general chemistry and things like that. Otherwise, in this class, most other equations and places where R pops up will want to use this 8.314 joules per Kelvin mole. You don't need to memorize the value on exams that would be given. But I tend to try to remember by remembering it as 8 point pi, right? Pi 3.14, blah, 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 right? If I remember, it's 8.314. But anyways, all right, we just got to plug in for R. Okay. 8.314, and our temperature 0.042 times the temperature of 359 Kelvin. 643 times 8.314 divided by 159 squared. Okay. And
0 between 3 and 16.30.
Oh, is there? Okay.
You wrote it on the one above it.
I did, yep, and I forgot it on subsequent lines. Thank you. Yeah. Right.
So do we square the 0.021 as well as the t?
No. So how that's written, I'll go back to sharing this right. The square is just on the t. I tried to make sure there's a space here to help, indicate that just t squared and nothing else. So yeah, so 0.021 was never squared in this problem. So yeah. Now my handwriting might not be as clear, but at least when the problems are typed up and things like that, I try to make sure that it's very clear that it's just t squared times 0.021. Other questions? Yep.
How do I understand the units of T?
Yeah, I was hoping people. So a lot of times in these things, and we'll deal with this more when we talk about like some other things with partial molar volume of liquids and certain things. There's going to be a number of times in this class where there'll be equations like this. So the way these equations are typically written is you'd have something like 3 halves R times T 0.021 T squared, and then you multiply this by like joules per Kelvin squared or something like that, plus 6430 R divided by T, and this is divided by like Kelvin. Like a lot of times how these equations will be written to like ensure units and things like that is that you'd like just multiply or divide by the actual units that are needed to make them work out. And there's a number of cases, both by myself and even in the book and things like that, that a lot of times it just sort of washed out, kind of just assumed like, you know, they're the appropriate units here to make sure that everything cancels out to the units it needs to be. But yeah, I can do a better job of trying to make sure to specify something like that. I kind of thought about it sometime later after I made the quiz, but was thinking, well, hopefully no one really pays that close of attention. So I apologize if that was a little confusing in the problem. But yeah, that's often what's done is, you know, just like, for example, right, in your equilibrium constant, right, talking about in general chemistry, right, technically the pressures and concentrations are divided by like a bar or a 1 molar or things like that to make sure that thing's unitless, right? But you never write like concentration of you know, NH4 plus divided by 1 molar, you know, and blah 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 in your like actual expression for K. It's just sort of assumed that the units are kind of divided out to make things work. So yeah, that's kind of what I did here. Is I just left out that, but yeah, that's if I wanted to write things precisely, that's how it should have kind of been written. Other questions? Yeah, I will double check answer here. So I'll look at the answer on Canvas, make sure. As we were writing this out, I don't know, for some reason in my head, I got the inkling that I did something wrong there when I calculated the answer. So I will double check my answer after class and update the quiz. All right, anything else? Not on the, okay, but some of the other questions, right? I'm just curious about something. One time. Yep. All right. Oh. Okay. All right. So question number 2 then. I mean, 2, 3, and 4, right, are the exact same problem. I'm just asking for change in internal energy, work, and enthalpy. Right. So. Screen sharing now. Oh, I'm still sharing that. Okay, sorry. Let me back to sharing this, right? So is there one of those 3 values or all 3 that people are interested in seeing? Yeah, 0.5. Constant pressure of maintaining mechanical equilibrium. The external 1 ATM. 2.25 liters. Sorry, I'm writing down kind of the information here. The final equals 9.3 liters. All right, and the question is, what is delta U? Kilojoules. All right, so, right, we're interested in that change in internal energy for a process where you're expanding against a constant external pressure, right? So it's a constant external pressure expansion, but you're also in mechanical equilibrium. So this is essentially like, you know, the example I always go to is thinking of heating up a balloon, right? If you try to expand a balloon, right, it's always at constant pressure and has the pressure equal to the atmospheric pressure. And the only way to expand it is either add more gas or to heat the balloon up, right? Increase its temperature. Okay? And so that's essentially what's happening here. So you're heating up a balloon, causing it to expand, causing then a change in its internal energy. Okay. Right? And so what right? So what equation do we use to calculate yeah, I'm going to put NCVM here, delta T, because I think in the problem I said that was CV equals 3 halves R. If you look at the units, this is joules per Kelvin mole. So this should be CVM, okay, right? M heat, like, yeah, this heat capacity is per mole. Yeah, sorry. Yeah, I need to. Yeah, well, because here the units are built into R. R has units of joules per Kelvin mole, and so, but yeah. So, but okay, no need to multiply by n. Now you can do this by calculating what the initial and final temperatures are, right? But we can use the fact that ideal gas law PV equals nRT. Okay, temperature's changing, and the only other thing that's changing is the volumes. This NCVM times that change in temperature, right, is right T final minus T initial, right? If I rewrite my ideal gas law, okay, right, I can get temperature from the ideal gas law as PV over NR, okay, and so this is just the pressure times the final volume over NR minus pressure times the initial volume over NR. And so I can actually solve this equation for delta U. The pressure is the same, constant times N times CVM over NR times delta V. Okay. Right. N's cancel here. And then if I use my R, because I have pressure in atmospheres, volume in liters, so if R is, so if I like plug in things, right, this is 1 ATM times CV here is 8.314 joules per Kelvin mole. Oh, thank you. Yep, 3 halves. Thank you. And then if the R here I use in the bottom is 0.08206 liters, atmospheres, Kelvin mole. Okay. And then I did not give myself enough room here. Crap. Right. I should then also multiply this top by the change in volume, which is what, 6.95 liters. Okay. So I apologize for not really giving myself enough room to write this out all the way. But if you look at the units right now, then the atmospheres cancels with the atmospheres, liters cancel with liters, and then this per Kelvin mole will cancel with per Kelvin mole, and these things, and what you're just left with is joule, right? And so delta U is 1 times 8.314 times 3 halves times 6.95 divided by 0.08206. And I'm also, right, and this is going to give me an answer in joules, right? And so the final answer needs to be in kilojoules, so you need to take this number and divide it by 1,000, right? Final minus initial, CV, 2 and 4, the answer is negative. Delta T, temperature should increase because the volume is increasing, so it should be a positive All right. Yeah, no, it should be a positive value. Really make that negative. All right.
Yeah.
Check this out.
Yeah, it's the value set.
Yeah, do have negatives. So did I write something wrong with the problem? See, volume, no, it's a volume increase. So the internal energy should, volume increase, it does do work. Work should be negative, but delta U is positive because the temperature increases. Yeah. So now that should be a positive value. Oh. Okay. All right. Way to do that. I don't know. All right. So where did I get that 0.65? 695, right? So that was from the change in volume, right? So, right, my initial volume here, right, my final volume is 9.3. I subtract off the initial volume of 2.35. That is my change in volume, which is 6.95 liters. So that's where I got that number from. Okay. So for work, for the next part, right, the work is just equal to minus P times delta V, which is minus 1 times 6.95. And then we need to convert that to joules by multiplying by 101.325. Okay. And then you can divide this entire thing by 1,000 to convert that to kilojoules, right? So that will give us the work in kilojoules. Okay. And then delta H here is going to end up being the same thing as kind of delta U, except R, the Cp for an ideal gas is equal to 5 halves R if Cv is 3 halves R, right? So right, the molar heat capacity at constant pressure is equal to the molar heat capacity at constant volume, right? Cvm plus R equals Cpm, right? And so, right, this is going to be kind of the same equation up above, which will have like pressure times N times Cpm for NR times delta V, right, which is 1 times 8.314 times 5 halves times 6.95 divided by 0.08206. And I guess 1,000 here if I want to convert this to kilojoules. Right. So yeah. That's how we get delta H, work, and delta U. Questions? Huh? 5 halves. So I know, so for an ideal gas, this is always true. And in the problem, you're told CVM is 3 halves R plus R is equal to 5 halves R, which is CP. So So 3/2 R is the heat capacity for a monatomic ideal gas. And so that's a very common heat capacity that will be used in all problems. It's just, you know, a monatomic ideal gas, 3/2 R, get the heat capacity. Yeah. No, that was already brought up. The answer should be positive in these.
So I did something kind of weird. I went CP. I used CP equals CP plus NR.
Yeah.
So I divided CP by, or multiply CP by the moles.
Yeah.
And
Uh-huh.
then just use the CP. So I guess it would be molar.
No, that wouldn't be the molar, and that's fine. You can do that. It's just like, I mean, did you calculate the final and initial temperatures when you did it? Huh?
The answer was the same. I'm just wondering
Yeah.
if that's like actually in biology.
Yeah. Yeah. No, there's a number of ways to go about solving these problems. How I present the solution is not the way to do it. It's just the way I think of to do it at the time. But there's multiple ways to go to solve a problem. And yeah, right. Questions on the you know, homework and exams and things like that are path independent questions, right? State questions, if you will, right? Doesn't matter the path you take, as long as you end up at the same answer, it's fine. All right.
You said you don't have to memorize the values of R. Are you giving us the units for those?
Yeah, those will be given as well. Like, I mean, the constants will be given with their units and things of that nature. Yeah. So, but you will become very familiar with it as the course goes, because most problems will involve the ideal gas constant, and so it will become kind of a familiar question. So, all right. Other questions? All right, so since we can, I'm going to actually just have us talk about the question we didn't get to last time, which was, suppose we have a temperature-dependent heat capacity, right? And we want to know what is the enthalpy change given that temperature-dependent heat capacity when I go from 298.15 Kelvin to 300.15 Kelvin. Right here, right, how the equation's given is the units of A, B, and C, these constants, right, have built-in units to make everything work out. Yep, exactly, right? So if I wanted to solve this problem, right, so CP is A plus BT plus C over T squared. Okay. If I wanted to solve for delta H for this problem, right, delta H in general is integral of CP dt, right? If CP is a constant, then that's just CP delta T, right? In this case, CP is not a constant, and so this is the integral of A plus BT plus C over T squared dt, right? From some T initial, T final, right? And so to solve that, we have delta H, right? The integral of A, right, just a constant, gives us T. So this solution of this is AT. Integral of T is T squared over 2. So this is plus B over 2T squared. And then the integral of negative, or 1 over T squared, sorry, gives us a minus 1 over T. Okay. Right, so should be good, right, on all that. And then I evaluate this on my initial and final temperatures, right? And so that delta H, right, is AT final plus B over 2T squared final minus C over T final, right? Minus A over T, A times T initial plus B over 2 times T initial squared minus C over T initial, right? And I plug in the numbers, right, in order to get the answer. And I'll show the numbers in a second. They're on the slide. But any questions about how we did this, right? Again, we start with the fact that delta H is, right, related with integral Cp delta T, right? And we get even started from the initial thing of dH equals Cp dt, right? Get started here. We wanted to, and then just integrate both sides, right? Integral of delta of dH is just delta H, the state function, and then integral of Cp just depends on what the actual value of Cp is. Okay. Question? All right, right. So if you plug those things in, right, what you'll get is for the first term, you'll get roughly 2,143, then plus 189, and then minus 32.7. Get a final value of 2,299.6 joule. All right. Other questions before we get going here? About anything or other example problems people want to see? The concerns they have? All right, so let's review some of the things we've talked about so far. We've talked about reversible expansions. What is a reversible expansion? Kind of try to describe a reversible expansion. Yeah, right. You're in mechanical equilibrium, right? The internal and external pressure are the same, right? Right, and right again, the reason why you're in mechanical equilibrium, right, and the internal and external pressure are the same is because, right, a reversible change, right, is always at equilibrium, right? A reversible change in state maintains equilibrium throughout. That change equilibrium, chemical, mechanical, thermal, whatever. Equilibrium is maintained. Right. For isothermal changes, what does that mean? Yeah, constant temperature, right? And then adiabatic changes that we're talking about today mean what? Yeah, no heat is transferred between the system surroundings. Q equals 0. Right. So again, right, adiabatic means Q equals 0. Right, so let's consider the adiabatic expansion of an ideal gas, right? Ideal gas law, PV equals nRT, okay? Right. So what questions do we know about, right, if I'm expanding an ideal gas, what equations would I know that relate to work?
Equals negative nRT.
LNV funnel initial, right? Yeah. So right, for an isothermal reversible expansion, right? And where did that kind of equation come from? If I'm looking at just an infinitesimal change in work, it's related with what? dW equals, yeah, so right, and that was the other question I was going to get at, right? That some small change in internal energy is related with some small amount of work done and some small heat that's transferred, right? That small amount of work. It's also related with minus P external dV, okay? But, and we'll get to that in a minute, right? But we can first look at, right, some small amount of heat or internal energy change related to heat and work, right? Since there is no heat transferred, right? Q is 0, dQ also has to be 0, okay? And then we know for an ideal gas that du is just CV dt, right? Again, it doesn't matter if it's being done adiabatically or anything else, right? Du is always CV dt, okay? But because we're doing things adiabatically, du also happens to equal dw, right? So the work that's done adiabatically is just CV delta T, okay? Assuming CV is constant, right? Which is also equal to delta U, right? Delta U is CV delta T, and work is CV delta T, right? They have to equal each other because there is no heat transfer for this process, right? Because it's done adiabatically. So these things have to equal. Any questions about these statements? All right. So, right, the final question here is, right, how do we calculate that change in temperature if we're not given it? And we'll get to more specifically how it's done. But first, I want us to just think about what do we expect the sign to be for a change in temperature for a gas, right, that expands adiabatically. Okay? Do you expect as you increase the volume of your ideal gas, right, adiabatically, that the temperature will increase as well, or that the temperature would decrease? So decrease. So why do you think it will decrease? Yeah, right. And so yeah, so right, the temperature change has to drop because your gas is doing work, right? As it's expanding, it has to be doing work on the surroundings, right? The work is being done by the gas, which means its internal energy has got to be decreasing, right? Because if it's doing work, it's giving up some energy to do that work, right? Push a ball up a hill, right? You're doing some work, you're giving up some energy in order to push a ball up a hill, right? And so the gas is giving up some of its internal energy in order to do this work, okay? That internal energy cannot be replenished via heat, right? Because this is done adiabatically, right? Q is equal to 0, things are done adiabatically, so I can't get back some of that internal energy as heat. And so in this case, the only place that internal energy is coming from, right, for an ideal gas is through its kinetic energy. Kinetic energy's got to drop, right? So its average temperature is going to be dropping, right? So the temperature of an ideal gas as it expands, right, is going to decrease when it expands adiabatically, okay? Right? Which is, right, and if I think of my ideal gas law, right, PV equals nRT, I'd say, well, volume is increasing, right, on the left side of that equation, right? I have temperature on the right side. Shouldn't temperature be increasing, right? But again, in this case, it's not, and that's because as volume is increasing, both temperature and the pressure are dropping, okay? So for an adiabatic expansion, your volume, when it increases, has a decrease in temperature and a decrease in pressure, right? And the fact that the temperature is going down means that that pressure drop is very significant compared to, say, the volume increase, right? Because you have some number that's getting smaller, the pressure's dropping as the volume's getting larger, right? So that pressure's got to be dropping faster than the volume's getting larger in order for the temperature to be decreasing, right? If that makes sense, right? Let me just write out our ideal gas law. Or actually, let me guess that. Ah, shoot. Buttons. What have I done? I'll go back here. Share that. So I can just go back one slide, right? Our ideal gas law, right? Right. So if volume is increasing, right, and pressure is dropping, right? And the fact that temperature is also dropping means that pressure's got to be going down pretty quick as this volume is increasing, okay? In order for our ideal gas equation to hold, right? Which it has to always remain valid, right? PV always has to equal nRT, okay? So again, we have a drop in temperature for an adiabatic expansion, okay? Because the gas itself is doing that work and it's giving up its internal energy to do so, which is causing it to drop in temperature, okay? All right. So how do we calculate that temperature? Okay. Well, we're going to assume here that not only am I expanding my gas adiabatically, but I'm also going to do it. So I can use the fact that P external equals P, which again, from my ideal gas law equals nRT divided by V. Okay. Right. I have that equation from previously, dW equals CV dt, because again we said du is equal to dW because dq is equal to 0, right? Some change in internal energy is related with the change in work, because the change in heat is equal to 0. Okay. Again, I know in general for expansion work that dW is also equal to minus P external dV. Well, I can just plug in nRT and do dV divided by V, right? So I can plug in the fact that the external pressure is equal to the internal pressure, which is nRT divided by V, right? I'm going to define some random constants here, C, which is CV divided by NR, or CVM divided by R, okay? And what you get, say the math is worked out on the slides, videos online. Won't go through working out all the math here, okay? But basically, if we set this dW equal to that dW, right? The adiabatic work is the same as the work here, right? So I CV dt equals minus nRT dV divided by V. You integrate both sides after rearranging the equation a little bit. You'll end up with this final equation, which tells me that the final temperature is equal to the initial temperature times the ratio of the initial volume divided by the final volume, all to this 1 over C power, which again, C is just the heat capacity of the gas divided by R. Okay. Again, so for here, CV is typically joules per Kelvin, so the R you'd use would be the joules per Kelvin mole. Yeah, 8.214. Yep. So again, you could use either R, it's just you have to make sure the units of that R would be the same as the units for the heat capacity. But yeah. So, other questions? Right, and if you use the ideal gas law, again, I'm not going to go through the derivation here in class, but let me look. You can also relate what that change in pressure is between the initial and final pressure. Right, I guess I could have rewritten that equation, right? Saying P final equals P initial times the ratio of the initial over final volume raised to this gamma power. Gamma happens to equal the molar heat capacity at constant volume. Plus R divided by the molar heat capacity at constant volume, okay? Which for an ideal gas is just Cp divided by Cv, okay? For a monatomic ideal gas, it comes out to be 5/3. But, okay. These equations for like temperature, like pressure here are not something you'll have to memorize. You'd be given those when needed on an exam, okay? Right? On homework or online quizzes or things like that, you can use whatever notes or resources you want. So a lot of times they're not given because just assume you'll look them up if you need them. So questions about these relationships. Again, notice, right, that the final pressure and final temperature, right, are related with the ratio of the initial volume divided by the final volume, right? So if you have an expansion, the initial divided by final volume is a number less than 1. So both the pressure and the temperature will decrease, right? Because you're multiplying the initial pressure and temperatures by some number less than 1, right? Well, if you're doing a compression, right, then the initial volume is greater than the final volume. So that ratio of initial over final will be greater than 1, and then your temperature and pressure will increase. Okay. Right. And yeah, and the change in pressure is always greater than like the percent change in pressure is always greater than the percent change in volume. If you're to compare the coefficients like 1 over C versus gamma, you'll see that the gamma is always a larger number. And so the change in pressure is always greater than that change in temperature, which again, it needs to be for things to kind of work out in the ideal gas law. So, yeah.
For the T final equation, is D initial divided by T final raised to the power of 1 divided by C?
Yeah.
Okay.
Yep. Yeah. Yeah, and this definition of C and gamma is just kind of what's used in the book and in places. So I'm just kind of putting it here. I don't know why. Like, I don't know why putting 1 over C versus like R over CVM is that much better.
Right.
But, you know, it is what it is. It's just a common thing that's used. So I'm just putting it. So you at least see where it is. And if it's confusing, you can ask me about it now, right? Instead of seeing it pop up on a problem somewhere, being like, well, what the heck is lowercase c? And you don't have to memorize what gamma or lowercase c is here. That would be something that's given. But yeah. Other questions about this? Right. So, right, on the lecture videos online, I talk a little bit more about the relationship between adiabatic and isothermal. So we'll just kind of review that relationship by looking at a question here, right? I assume I have a reversible expansion that's done of an ideal gas where one of the expansions is done isothermally, the other expansion is done adiabatically. The question is which expansion has more work being done on the surroundings, the adiabatic, the isothermal. We need more information, right? We can never know, or they're equal. Anyone have any thoughts? And someone saying adiabatic here. So what? Right. So let's kind of take a step back. Right. When I have some function, right, and I'm say integrating that function, what is that integral giving me? If I have like a plot of that function, the area underneath the curve, right? Right, and work is related with pressure as a function of volume, P dV, right? And so the work that's done by a gas, if you plot pressure versus volume, is just going to be related with the area underneath that curve. So knowing kind of the work is related to the area underneath the curves, which one of these things does more work? Isothermal, right? Isothermal does more work than adiabatic expansion, okay? Right? Right, you can kind of think of that as, right, I mean, the biggest reason why is just because the pure fact, right, that for an adiabatic expansion, your pressure drops much more rapidly than your isothermal expansion because the temperature is also dropping. Okay? Since the temperature is dropping for an adiabatic expansion, right, just assuming constant volume, right, a drop in temperature would correspond to a drop in pressure. So the fact that the volume is increasing and the temperature is dropping means the pressure is dropping even more rapidly than a isothermal process where the temperature is the same and the pressures and the volume is just increasing, right? One case, you have in both cases, volume is increasing, right? They're increasing by the same amount. But in one case, the temperature is staying the same, while the other case, the temperature is dropping, the pressure is decreasing even more rapidly, again, for that adiabatic expansion, which again, you can see in this plot, right? That the pressure drops more rapidly for an adiabatic expansion. Okay. Other questions? All right. So again, here it's isothermal, right? More work. Right. So as we've been talking about, right? So I have a gas, and I condense that gas to a smaller volume adiabatically and reversibly. What will happen to the temperature? Will it increase, decrease? Depends on the initial and final states. Cannot be determined, or the temperature will not change. One person saying the temperature will decrease. Most people agree with that. Anyone have any other thoughts? You got increase as well, right? Right. So yeah. So right, if we think about this, right, so you can look at the graph, and we can do both. So first, I'll just talk about it conceptually, right? So I have an adiabatic compression, right? If I'm compressing my gas, that means I'm doing work on the gas, which means I'm providing energy to my system, right? If I'm putting energy into my system and I'm not allowing any heat to transfer out of the system, then the temperature in the system must increase because I have to have an increase in internal energy, right? And for an ideal gas, an increase in internal energy is corresponding to an increase in temperature, right? And they're proportional to each other with the heat capacity constant volume being that proportionality constant, okay? And so in this case, if internal energy is increasing, temperature is increasing, right? So A here, it's got to increase, okay? Also pictorially, right, what we can look at is we're looking at what? A decrease in volume. So if I, right, in this plot, they end up with the same temperature, or yeah, same temperature here and pressure and volume at this point, but you're at two different points here, right? For the isothermal, the temperature stays constant, right, for that compression, but we see here for an adiabatic compression, in order to get to this point here, right, we have to decrease the temperature, right? We got to increase, right? We got to increase our temperature as we're compressing, right? So as you're going to smaller volumes, as you're going to the left in volume, temperature's got to increase as well. Okay. So again, A here, increase. All right. As a final kind of review of just some of the conceptual things of what's going on in the problem, right? If I have an ideal gas and I expand it to a larger volume, adiabatically and reversibly, which one of the following is always true? A, work equals delta U. B, delta T is greater than 0. C, Q surroundings is less than 0. D, pressure times volume equals a constant. Or none of these are always true, or maybe some of them are true. So for an adiabatic expansion, is work always equal to the change in internal energy? Yes, because the internal energy is always equal to work plus heat. For an adiabatic expansion, heat is 0, so A is always true. B here, if I'm going to a larger volume, expanding my gas, is delta T always greater than 0? No, right? As we've been talking about, right, the volume increases corresponds to a temperature decrease. So B is false. C, Q surroundings is less than 0. Sorry, I heard a lot of things at once here. Yeah, it's equal to 0, exactly, right? That is false, right? Right, Q surroundings is minus Q system, right? Both of which are equal to 0, okay? Both things are 0, right? So it's not less than 0, it is 0, okay? I can't have heat transfer in and out of my system, right? If I have no heat transferring in and out of my system, then the surroundings can't have any heat transferring in and out of it, right? Because those are the only two things we have in the universe, our system and the surroundings, right? So energy is going from one thing to the other, right? There's nothing else, right? I don't have systems or 3 surroundings or something like that. There's one system, one surrounding. Any heat that transfers is transferred between those two things. Okay? So C is false, right? Q is always equal to 0, as well as Q surroundings, right? D here, pressure times volume is equal to a constant. Nope, that's not true. Right, yeah, exactly, right? Pressure times volume is not equal to a constant because the temperature changes, okay? Pressure times volume to the gamma power, something like that, yeah. P times V to the gamma power ends up equaling a constant, but not P times V itself. Okay? And so yeah, so only A is always true. Okay, so the answer here is A. All right. Another set of statements again for reversible adiabatic expansion of an ideal gas. Which statement are always correct? Okay? A always true, B, C, D, or none of these. Okay? Yeah, so D here, right, is the only one that's always true, right? Because Q system and Q surroundings are both equal to 0, so that's true always. Okay. C is not true because there's no change in number of moles of gas or things like that. So C is not relevant, not a thing at all. Temperature is not constant, right? Because we're doing this thing adiabatically, not isothermally. And work is definitely not equal to 0 because I'm expanding my gas, right? So only D here is correct. All right. So now a numerical example here, right? Consider the adiabatic reversible expansion of 0.02 moles of argon initially at 25 degrees Celsius from 0.5 to 1 liter. The molar heat capacity, CVM, is 1.5 R. Okay. Question is, what is the final temperature? What is the work done? And then what is delta U, delta H, and Q? And for those on Zoom, I'll create a breakout room if you want to discuss the problem at all. You don't have to, but I'll open it up in case you would like to. All right. So, all right, to do this problem, right? First part of the question is what is that final temperature, right? We're told what the number of moles I have, told the molar heat capacity at constant volume, told the initial temperature, initial volume, and final volume. Okay. 0.5 liters and 1 point L. This is also an L. Right. Right, so that relationship for the final temperature is just the initial temperature times the initial volume over the final volume times 1 over C, which was R divided by CM. Okay. Now note here, the temperature is given in Celsius. We do not want to use Celsius. We want to use Kelvin. Use Celsius, you will get a very, very different answer. So the temperature initially in Kelvin is 25 degrees Celsius plus 273, right? So 298 Kelvin. Okay. And so the final temperature is equal to 298 times 0.5 divided by 1.0. And then CVM is right, it's 3/2 R. This is just to the 2/3 power. Okay. And that will give us our final temperature rate, which is 298 times 0.5 to the 2/3 power. Okay. Which I'm going to go back slide real quick so we can get what that number is. Okay. So that final temperature is equal to 187.82 Kelvin. Okay. Here, well, you don't need it. I calculated the initial and final pressures as well, right? Just you can kind of see, right? The pressure goes from about 1 atmosphere, 0.3 atmospheres. Again, temperature goes from 298 to about 187. All right. So the second part of the question, right, was calculate the work done. Okay. Right. We know for an adiabatic expansion, work is just the same as the change in internal energy. Okay. Which the change in internal energy I can write for an expansion or compression of an ideal gas. It's just CV m delta T. Okay. Yeah. Times n. Yeah. And so this is equal to 0.02 moles times 3/2 times 8.314 times our change in temperature, which is what, 100 and okay. So negative 110.3. Okay. So I'm going to write that again just so I have more space, right? 0.02 moles. Now we can put units to remind ourselves times 3/2 times 8.314 joules per Kelvin mole times negative 110.3 Kelvin. Okay. And so plugging in those numbers, so I'll go back to the slides here since I have the numbers. The current straight, so 0.1, 0.02 times 1.5 times 8.24 times that change temperature gives us minus 27.51 joules. Okay, so that is the change in work, or that's the work done, sorry, and also the change in internal energy. Now to get the enthalpy change, okay, it's just the same equation that we kind of use for the internal energy, just with the heat capacity at constant pressure, okay, for the constant pressure heat capacity, right, which is just 5 halves of R, right? So again, for an ideal gas, right, this is always true for an ideal gas, CPM equals CVM plus R, okay? It's always true for an ideal gas, okay? And so in this case, right, we get, right, and this thing equals delta U, and to get delta H, we just do NCPM delta T, right? Same number of moles, same change of temperature, and CPM is just 5 halves R instead of 3 halves R. Questions about this example problem here? And remember, when solving for that final temperature, to convert your temperature to Kelvin. Okay. I mean, for any problem in this class, convert your temperature to Kelvin. Okay. It's, there may be some examples where you don't need it in Kelvin, but just put it in Kelvin. Okay. Even if you could do it in Celsius, put it in Kelvin. It's a good habit. Make sure you use it. All right. Here. So yeah. So here we have the adiabatic expansion of 0.02 moles of argon. So same number of moles, same initial temperature, same initial volumes, same final volume. The only difference here is now I'm expanding against a constant external pressure of 0.308 atmospheres. Okay. Which if you noticed in the previous problem, that was the final pressure of our adiabatic reversible expansion. Okay. Our reversible adiabatic expansion's final pressure was 0.308 atmospheres. Okay. So I'm expanding to against that final pressure. Okay. And then the question is for this problem, what is work? What is delta U? What is delta H? And what is Q? Okay. So first thing given here is work. What equation would I use to calculate work for an adiabatic expansion against a constant external pressure? So yeah, so we got minus P external delta V. Any other equations or thoughts I could use to calculate work? What else is equal for an adiabatic expansion? Delta U, right? And we don't necessarily need to use that right now, but just as a reminder, right? Work equal to delta U, which is N CVM delta T, and work also in this case for a constant external pressure is minus P external delta V, right? So for this problem, right? For an adiabatic expansion, I know this is true, but I know also for a constant external pressure, this is true, okay? And I'm going to want to use this equation, right? Because I don't know what my final temperature is, okay? We're not really given the final temperature, okay, in this expansion. We don't necessarily know what it might be, and so we are given, however, the external pressure and the changes in volume, so I can calculate work this way, right? So the work for this problem is just going to be minus 0.308 times the change in volume, which is going to be 0.5 times, then I'm going to convert this from 1.325 to joules. Okay, so I multiplied that 101.325, right? This is the joules, sorry, this is the liters, atmospheres to joules conversion, right? That's where I get this number here. Okay, so I'm converting my liters, atmospheres to joules. Okay, so going back to this, right? Again, my work minus P external delta V, converting that to joules is minus 15.6 joules, the amount of work that I did. Right, Q is equal to 0 because it's adiabatic, right? So delta U is equal to work, right? So already, right, and these things we've got to calculate. Work, we already calculated, right? That minus P external delta V, which also happened to okay. So I have delta U as well, and then Q is equal to 0, right? Because it's an adiabatic process, okay? To get delta H, right? Again, right? Let's think about equations we know, and we know delta U is equal to this, okay? Which also happens to equal minus P external delta V. Delta H, I know to calculate that, I need to use this NCPM delta T, okay? Right? But again, I don't really know what delta T is, right, given in the problem. But again, I know delta U is equal to this, right? But it's also equal to work, which is equal to minus P external delta V, right? So I know that NCVM delta T equals my work, right? Equals work, which was, now I should write down that answer here, was minus 15.6 joules. Okay. Right? So I can solve for my change in temperature, right? I can divide CVM and N onto the other side, and I get delta T equals minus 15.6 joules over 0.02 moles times 3/2 times 8.314 joules per Kelvin mole. Okay. So writing up those units, right? So again, I get 15.6 joules divided by all this stuff, right? Units will all cancel, and I'll just get left with Kelvin. Okay. So then that gives me my change in temperature, right? And actually, if I wanted to, I could plug that back into the delta H equation here, right? And have delta H equals 0.02 moles times 5/2 times 8.314. Again, CP is just CV plus R. Okay, that's how I got that, joules per Kelvin mole. Okay, times my change in temperature, which happens to equal minus 15.6 joules over 0.02 moles times 3/2 times 8.314 joules per Kelvin mole. Okay. And so if you notice, actually, the 0.2 moles cancels 0.2 moles there. R cancels with the R there. Okay. And you end up with delta H equals minus 5/3 times minus 15.6 joules. So you could avoid calculating delta T if you wanted to by plugging that in. You'll kind of find that relationship. After you can solve for delta T and then plug that in, right? So I actually calculated the final temperature. You're not asked to, but I actually calculated that final temperature using the equation we had, right? And then again, delta H, you take this and divide it times it by 5/3 and you'll get 6 joules. Okay. Right. And I calculate things like the final temperature, right? To note that the final temperature here, right, decreased for this adiabatic expansion as we expect, but decreased less than it did for the reversible, right? And it's because we got less work done by the constant pressure expansion versus the reversible, right? So this goes back to the point, right, that any reversible process always does more work than an irreversible process, okay? The most work you can get out of something is if you do that change in state reversibly, okay? So reversible isothermal expansion produces more work, right? And for an adiabatic reversible isothermal, or not isothermal, sorry, the reversible adiabatic expansion, you get more work than an irreversible adiabatic expansion, which means that the temperature change is less for the irreversible case than it is for the reversible case, okay? And again, I also want to highlight, right, that in this problem, when I do a adiabatic expansion against a constant external pressure, we cannot use, right, this equation here to calculate the temperature change, because this equation assumed a reversible expansion, okay, right? It assumed reversible adiabatic in order to get this equation, but we do not have a reversible adiabatic expansion in this problem, right? We have an adiabatic expansion against a constant pressure, which is not reversible. Okay. All right. Those, right, and then so we can do more problems with this, and we'll revisit these problems as well again when we talk about entropy, and you're just doing examples later on, right? But you know, those are the two types of adiabatic expansions you can have. You can have a reversible adiabatic expansion or constant pressure, at least for the sake of this class. Okay. And that's it for kind of examples in today's lectures. Meet again on Wednesday. Okay. If anyone has any further questions, I'm happy to answer them, but you're welcome to leave or leave.